What is fire? The first step in knowing how to prevent fire is to understand how fire occurs and the difference between various. In this film, we will point out the elementary principles of combustion, illustrate how solids, liquids, and gases, and explain the character of dust and gas explosions. The rusting of iron is a slow chemical reaction between the metal and oxygen in the air. The iron and oxygen combine to form iron oxide. This is slow oxidation, which destroys metal just as fire destroys wood. Like all other oxidation, rusting produces heat, but so slowly there is no increase in temperature. Like rusting, fire is also a process of oxidation. We can burn metal if it is finely divided like steel wool. In contrast to rusting, fire is rapid and produces heat, which is evident. Let us see how heat is produced by oxidation. Suppose we saturate some cotton waste with linseed oil and put it in a pail. At the start, the temperature is normal. Gradually, however, the linseed oil oxidizes, producing heat. Because the heat is held in the waste, the temperature gradually rises. The waste finally becomes so warm, it begins to char and give off smoke. The increasing heat speeds up the oxidation, and finally the waste becomes so hot that it bursts into flame. By this simple demonstration, you have seen how spontaneous ignition occurs. When a wooden splint burns in air, we have very rapid oxidation or combustion. Air contains about 20% of oxygen, which makes the combustion possible. Let us now see what happens when the splint burns in 100% or pure, and insert the glowing splint into the oxygen. Immediately the splint bursts into flame again, burns rapidly, and then goes out as the oxygen is exhausted. The speed of combustion or burning depends upon the amount of surface exposed to oxygen. You all know how difficult it is to ignite a log or a heavy chunk of wood. If, however, you chop the wood into kindling and then ignite it, it burns very easily. Now suppose we convert the wood into shavings. It ignites more easily and burns more rapidly. Going a step farther and grinding the wood into fine dust and sifting it over a candle flame, we see that it burns with explosive rapidity. This is because the total surface of all the particles exposed to oxygen is very great. By contrast, if the dust is in a pile, only a small part of all the surfaces of all the dust particles is exposed. And with this gas flame, which is invisible but very hot, the dust becomes difficult to ignite. If you stir up deposits of combustible dust into a cloud which fills a room or building and ignite the cloud, you have a dust explosion. In this building model, a dust cloud of cornstarch will be produced and lighted by a candle. When the dust was ignited, the instantaneous burning produced pressure which tore the building apart. Now note what happens if the windows and doors are arranged to swing open quickly. Watch for the explosion. The explosion venting windows promptly relieve the explosion pressure and no building damage results. Different dusts produce explosions of varying pressures. The greater the pressure produced, the more dangerous the dust. In the factory mutual laboratories, a test bomb in which dust-air mixtures are ignited and exploded measure the pressure produced and gives a reliable index of the hazard. We have seen how oxygen from the air takes part in combustion. Some materials contain oxygen for combustion. We are here making a solution of sodium nitrate. With which we will draw invisible lines on a piece of paper. After drying the solution on the paper, we will start a smoldering fire. Note how it follows the lines where the sodium nitrate was applied. This is because the nitrate gives up oxygen easily, which aids the smoldering fire to eat through the paper. The familiar red light flare contains its own oxygen supply in the form of sodium nitrate. Thus, it continues to burn inside the tube, even in a downpour of rain. These firecrackers contain potassium nitrate, which supplies all the oxygen needed for instantaneous combustion. Pyroxylin materials, such as the familiar celluloid, also have oxygen which is readily available. Suppose we insert an electric heating coil in a small drum of this material. And then momentarily plug in the coil. The heat from the coil starts to decompose the pyroxylin, giving off thick, poisonous, and combustible fumes. The decomposition produces heat, which further speeds up the decomposition. Finally, the increasing temperature ignites the gases spontaneously, and they burn violently because the pyroxylin itself supplies some of the oxygen necessary for combustion. Even water itself may give up oxygen. Suppose we ignite magnesium turnings and then play a spray of water on them. The hot magnesium decomposes the water, uniting with the oxygen and setting free the hydrogen, which then burns freely in air. We have seen how solids burn and how oxygen for combustion is supplied by the air and by some chemical substances. Now let us look into the burning of flammable liquids. The flask contains gasoline. When the flame is applied, note how the fire burns near the top, well above the liquid surface. With all flammable liquids, it is the vapor and not the liquid which burns, and the burning is similar to the burning of gas. The vapors of flammable liquids are mostly heavier than air, flow downhill, and collect at low points. Suppose we pour benzol on some cotton waste and put the waste in the top of the trough. The benzol vapor flows in a layer downhill under the middle candle without igniting and banks up at the bottom until the level of the vapors reaches the flame of the lower candle. Watch. The vapors flash back and ignite the waste. While liquid vapors are heavier than air, most combustible gases are lighter than air. We fill a balloon with hydrogen and release it. Since hydrogen is lighter than air, it ascends to the ceiling. This shows that in ventilating rooms where gases may accumulate, the air must be drawn from the top of the room. The hazard of a liquid is measured by its flash point, which is the temperature at which vapors are given off fast enough to flash if ignited. In this apparatus, the liquid is gradually heated from normal temperature until a flash is obtained when a small invisible gas flame is passed over the liquid. The fire point, which is the point where the vapors will continue burning when ignited, is usually a little higher than the flash point. Any liquid like kerosene, which has a flash point above ordinary temperature, is not normally dangerous. Liquids like gasoline, which have a flash point below normal temperature, are dangerous because only a source of ignition is necessary to start a fire. If now we heat the kerosene above its flash point, it does ignite readily. Just as dust mixed with air explodes, so vapors mixed with air explode if within the explosive range. If we put a few drops of dyed ether into this cylinder, it will evaporate and mix with the air. But in this case, when the spark plug is turned on, the mixture will not explode because there is too little ether vapor. If we use more ether so that the vapor concentration is within the explosive range, ignition sets off the explosion. If there is too much vapor in the air, the mixture will not explode in a closed container. It will, however, burn at an opening if a flame or spark is introduced, because at the opening there is a certain part of the mixture which is within the explosive range. We have now seen the nature of fires and explosions. It is equally important to know what causes fires so they can be prevented, and what forms of protection are available so fires can be extinguished. The factory mutual companies put fire prevention first. Their activities include not only tests on the hazards of materials, but also large-scale fire tests, research and development to help improve industrial fire